Welcome to our second lecture on fundamentals of transport processes. In the first lecture, we had considered dimensional analysis, and what I had told you was that a dimension is a measure of a quantity and the unit is the standard for measurement. A quantity has only one dimension. It could have different units, such as velocity has units of meters per second, kilometers per hour, and so on, but it has only one dimension, which is length per unit time. Okay. And the standard convention, the SI unit, in this SI unit of dimensions, there are 6 fundamental dimensions. These 6 are of course chosen subjectively, but they are considered, they are a standard by convention, okay, by international convention. The fundamental dimensions are mass, length, time, temperature, current, and light intensity. I will refer to the mass dimension as m, length dimension as L, time dimension as t, temperature is theta, and current dimension is ampere, okay, A. And in SI units, mass is kilogram, length is meter, time is second, temperature is Kelvin or degree centigrade, current is ampere, and light intensity is what is called candela, which we will not use in this course. So, these are the fundamental dimensions. Okay. All known quantities can be expressed in terms of these 6 dimensions. Okay. All known quantities can be expressed in terms of these 6 dimensions. And then we had gone to look at derived dimensions. Okay. How do you derive dimensions of other quantities from these fundamental dimensions? Basically from a relationship that involves known quantities and this unknown dimension. So, velocity is distance per unit time, length t inverse. Angle is the ratio of distance along the circumference of a circle and the radius. So, that is dimensionless. Angular velocity is has dimensions of inverse time, acceleration length t to the minus 2 because change in velocity per unit time. Force is mass times acceleration, ml t power minus 2, torque. Work is force into distance, ml square t power minus 2. Power is work done per unit time, ml square t power minus 3. Pressure, stress, etc. have the same dimension, force per unit area, m L inverse t power minus 2. Density is mass per unit volume, concentration is also mass per unit volume. And we had looked at some dimensions which are of relevance to this course. The mass flux, mass transported per area per unit time, m L to the minus 2 t inverse, mass per area L square per time. Diffusion coefficient was determined from Fick's law, which related the flux and the concentration difference. So, if I have 2 surfaces across which there is a concentration difference, okay, across which there is a concentration difference delta C, okay, separated by distance delta Z, the flux from one surface to the other will be directly proportional to delta C, the difference in concentration, inversely proportional to the separation delta Z. Constant of proportionality with a negative sign is what is called the diffusion coefficient, because transport occurs from higher concentration to lower concentration. And based on this, we had got the dimension of the diffusion coefficient as length square time inverse. Specific heat from the relationship change in energy or change in enthalpy is mass specific heat times the temperature difference, and we had got the dimension of specific heat. Okay. Heat flux is heat transported per unit area per unit time. Okay. Mass flux is mass transported per unit area per unit time, heat flux is heat transported per unit area per unit time, and from the dimensions of heat energy, area and time, the heat flux is m t power minus 3. Thermal conductivity is determined from Fourier's law of conduction, Q is equal to minus k delta T by delta Z, and from that we had got the expression for the thermal conductivity. So, these are relating to mass transfer and heat transfer. energy momentum transfer, okay, stress, okay, as we will see later in this course, stress is defined as the force per unit area, has the same dimension as pressure. Pressure is also a force per unit area. Okay. Both of them have dimensions of force divided by L square, okay, which is equal to m L inverse T power minus 2. The difference is that pressure is usually defined as acting perpendicular to a surface, whereas the stress acts parallel to the surface. Okay, that is the difference. However, the dimensions are the same, and this is also has dimension of has unit of Pascal in SI units, okay, which is kg per second square. Okay. Then let us look at the dimension of viscosity. Okay. How do you calculate the dimension of viscosity? From some relationship that contains viscosity and other known quantities. Okay. So, for example, if I had two surfaces, okay, separated by distance delta z, okay, and I will put a coordinate system here so that we can distinguish between the two directions. This along the surface, one direction along the surface I will call as x, the other direction perpendicular to the surface I will call as z, okay, and the separation between these two surfaces is delta z. Okay. And if one surface moves with a velocity delta V x in the x direction relative to the other surface, okay, in order to move two surfaces in a fluid relative to each other, you have to exert a force. Okay. To move two surfaces relative to each other in a fluid, you have to exert a force. Okay. The force per unit area for moving one surface relative to the other is tau xz, the stress or force per unit area, to be applied to the top surface to move it relative to the bottom surface, is equal to the coefficient of viscosity times delta V x divided by delta z. It is proportional to the difference in velocity, inversely proportional to the separation. Okay. This is Newton's law of viscosity. Okay. Newton's law of viscosity, okay, is directly proportional to the difference in velocity, inversely proportional to the separation. Okay. Therefore, the dimension of stress has got to be equal to the dimension of viscosity, the dimensions of delta V x divided by the dimensions of delta z. Okay. If I substitute all of these, dimension of stress is m L inverse T power minus 2 is equal to the dimension of viscosity. Velocity is length per unit time and divided by length, which is the separation. Okay. And from this I get the dimension of viscosity, m L inverse T inverse is the dimension of viscosity. This is 1 Pascal times 1 second. Okay. Some other mechanical quantities, okay. Surface tension is equal to mass, the surface tension is equal to a force per unit length. Okay. Stress is force per unit area, surface tension is force per unit length. Okay. Therefore, this has dimensions of force m L T power minus 2 divided by the dimension of length, okay, which is m T power minus 2, okay, because that is the dimension of surface tension. Okay. What is the dimension of elasticity? Okay, the dimension of elasticity is obtained from a relationship which contains this elasticity and other quantities. Okay. For this we need to define a relation for the elasticity, and that is that the stress is equal to the elastic coefficient, which I will call here as G times into the strain. Okay. What is the strain on an object? Okay. So, if I take an object and I apply a force on it, okay, if the original distance was L, okay, due to the force it stretches, okay, and the actual length becomes some other, okay, L plus delta L. Okay. The strain is defined as the difference in length due to this exerted force divided by the original length. Okay. So, this is equal to G into the change in the length divided by the length itself. Okay. That is the strain. The strain is dimensionless. It is the change in the dimension divided by the dimension itself. That is the linear strain. Area strain is change in area divided by area itself, the initial area. Volumetric strain is change in volume divided by the initial volume. Okay. So, that is the relationship between stress and strain that contains the coefficient of elasticity. Okay. Therefore, since this is dimensionless, okay, the elasticity coefficient has the same dimension as the stress itself, okay, which is equal to m L inverse t power minus 2. Okay, that is the elasticity coefficient. Okay. And finally, one important quantity that we will use, especially in when we study heat transfer, is what is called the ideal gas constant, or the Boltzmann constant. Okay. The thermal energy is given by the Boltzmann constant times the temperature, okay, where Kb is the Boltzmann constant. Okay. Therefore, the dimension of energy is equal to the dimension of Kb times the dimension of temperature. Okay. The dimension of energy is m L square t power minus 2, force into distance. Force is mass times acceleration. Okay. So, m L square t power minus 2 is equal to the dimension of the Boltzmann constant times theta. Okay. Therefore, the dimension of the Boltzmann constant is equal to m L square t power minus 2 theta inverse. Okay. So, that is the dimension of the Boltzmann constant. Okay. And the Boltzmann constant and the ideal gas constant R differ only by a constant number. Okay. So, for example, the ideal gas constant R is equal to the Avogadro number times the Boltzmann constant, okay, where the Avogadro number, if you express the ideal gas constant in kilomoles, it will be 6.023 into 10 power 26. Okay. Okay. Okay, or it is 6.023 into 10 power 23. Okay. In either case, whether you express in terms of kilomoles or in terms of moles, this is equal to a number. Okay. 6.023 into 10 power 23 molecules are present in 1 gram mole. Okay. Okay. Or let me be more precise here. okay, per this is the ratio of the mass of the molecule in kilogram of 1 kilogram mole in kilograms divided by the mass of the molecule itself in kilograms. Okay. So, this basically tells you how many molecules are there in 1 mole or in 1 kilomole. Okay. The Boltzmann constant divided by mass of one molecule is equal to the ideal gas constant by mass of 1 mole. Okay. Okay. The Boltzmann constant divided by mass of one molecule is equal to the ideal gas constant by mass of 1 mole. Okay. So, that is the relationship. This Avogadro number is just a dimensionless number, it is just a number of molecules. Okay. So, that is the relation, okay. Ideal gas constant and the Boltzmann constant. Okay. And I should just mention here that this Boltzmann constant is equal to 1.38 into 10 power minus 23, okay, joules per kilogram per Kelvin. Okay, that is the actual unit. Okay. This we will use later. Okay. Now, this dimensional analysis can be used to determine the dimensions of quantities which we may not be familiar with, so long as we have a relationship that relates that quantity to other such quantities. Okay. Let me take an example. Okay. I told you that for a Newton's law of viscosity, tau x z is equal to mu delta V x by delta z is the relationship. This relationship is valid for fluids that are called Newtonian fluids. Okay. The stress is directly proportional to the velocity difference, inversely proportional to the separation. There are more complex fluids that are called power law fluids, which satisfy a more complicated relationship. In this case, tau x z is equal to kappa delta V x by delta z into delta V x by delta z power n minus 1. Okay. Note that whereas Newton's law contains only one coefficient, the viscosity, this one contains two, kappa as well as n. Okay. Kappa is what is called as the flow consistency index, and n is what is called the power law index. Okay. So, these are the two coefficients. The power law index is dimensionless. Okay. You cannot raise a quantity to a power that has dimension. Okay. It has to be dimensionless. Okay. What is the dimension of this power law index kappa? Okay. How do we determine that? Okay. You can see that from this relationship, tau x z, the dimension of this has to be equal to the dimension of kappa times the dimension of, okay, delta V x whole power n divided by the dimension of delta z whole power n. Okay. Note that I have delta V x by delta z times its modulus to n power n minus 1. So, when you multiply these two, you get a power of n. Okay. M L inverse t power minus 2 is equal to kappa, okay, into L t inverse whole power n by L power n. Okay. This length dimension you can see will cancel out over here, okay, and I will finally get this kappa is equal to M L inverse t power n minus 2. Okay. So, that is the dimension of this flow consistency index. Okay. So, in this way, if we have a relation, we can determine the dimensions of quantities that we do not know. Let us take another example, and that is of electrical quantities. Okay. We will not be dealing with electrical quantities too often in this course, but we can still determine dimensions quite easily. Okay. So, the problem here is to determine dimension of charge Q, okay, voltage V, okay, resistance R, okay, capacitance C, and inductance L. Okay. So, that is what I would like to determine, okay, from known quantities. Okay. What we do know is the fundamental dimension, okay, current is ampere, okay. Current is ampere. Current is charge transported per unit time. Okay. Current is charge transported per unit time. Okay. So, therefore, the dimension of current, okay, which is ampere, has to have the dimension of charge transported divided by the dimension of time, okay, which means that the charge has dimension of ampere into time. Okay. A into t is the dimension of charge. Okay. So, knowing that current is charge transported per unit time, I can determine what is the dimension of charge. Voltage, okay. How do I determine the dimension of voltage? Okay. From a relationship which contains voltage and other known quantities. Okay. I know that power is equal to V into current. Okay. Dimension of power we had calculated, it is energy per unit time. Okay. Power is energy per unit time, which was mass length square t power minus 3 is equal to the dimension of voltage times the dimension of current, which is in amperes. Okay. Which means that the dimension of voltage is equal to m L square t power minus 3 A inverse. Okay. That is the dimension of voltage. Resistance, I know what is the dimension of voltage, I know what is the dimension of current, and you know Ohm's law, V is equal to I R, okay, where I is the current, R is the resistance. Therefore, the dimension of V, which is m L square t power minus 3 A inverse, is equal to the dimension of current, which is A, into the dimension of resistance, which means that the dimension of resistance is equal to m L square t power minus 3 A power minus 2. And the SI unit of this is ohm, SI unit of voltage is volt. Okay. So, we had calculated the dimension of charge, voltage, resistance, capacitance, okay, the charge stored. Okay. The charge stored is equal to the capacitance times the applied voltage difference delta V, okay, across a capacitor. Okay. Which means that the dimension of charge is A times T is equal to the dimension of capacitance times the dimension of voltage, which is m L square t power minus 3 A inverse. Okay. Which means the dimension of capacitance is equal to m inverse L power minus 2 t power 3 A square. Okay. I just divide throughout by the dimension of voltage. I am sorry, it should be t power 4. Okay. Because I have an AT on the left side and I have t power minus 3 on the right side. Okay. So, it should be t power 4. Okay. And inductance is determined from the rate of change of current. Okay. Delta V is equal to L times the rate of change of current with respect to time. Okay. Therefore, m L square t power minus 3 A inverse is equal to the dimension of inductance times A divided by T. Okay. Therefore, the dimension of inductance is equal to m L square t power minus 2 A power minus 2. Okay. So, that is the dimension of inductance. Okay. So, these are the dimensions of all the quantities that are used in electrical, all the electrical quantities. Okay. So, this is how you calculate dimensions. Okay. Now, next we will consider the dimension of an equation. Okay. All additive terms in an equation have to have the same dimension, and that is the dimension of the equation. Okay. For example, let us take an equation that you may be familiar with, the Bernoulli equation. P plus half rho plus rho g h is equal to P naught. P is the pressure, rho is the density, v is the velocity, g is the gravitational acceleration, and h is the height. Okay, so that is the Bernoulli equation. I have expressed it as the sum of additive terms. Okay. I have expressed, if in case you have some terms that are multiplied, for example, if I had rho into half v square plus g h, okay, then I need to expand it out. Okay, so that I get the sum of only additive terms. Okay. When written this way, for a dimension to be valid, each term has to have the same dimension, that is the dimension of the equation. Okay. Let us see if each term has the same dimension here. Pressure, force per unit area, okay. Mass L inverse t power minus 2, okay, that is the dimension of pressure. The dimension of the second term, half rho v square, okay. Dimension of density, mass per unit volume, okay, into the dimension of velocity square, L t inverse the whole square, okay. L square t power minus 2, okay, and you can verify that this has the same dimension, m L inverse t power minus 2, okay. L power minus 3 in the density, L square in velocity square. Okay, so, you get m L inverse t power minus 2. Rho g h, okay, is equal to m L power minus 3 into g is acceleration, L t power minus 2 into h as dimensions of length. Okay. So, m L inverse t power minus 2. And P naught is a reference pressure, it has the same dimension as pressure. Okay. So, clearly all terms in these equations have exactly the same dimension, and that is the dimension of the equation. Now, I should note that there are very often we deal with differential equations, okay, or integral equations. Okay. The dimension of a derivative is of a okay, for example, if I write a derivative with respect to the velocity of respect to time, okay, the dimension of any quantity divided by derivative is equal to the, okay, the dimension of this is equal to the dimension of the quantity divided by the dimension of time. Okay. The dimension of the derivative of any quantity with respect to any spatial coordinate is equal to the dimension of that quantity divided by the spatial coordinate L. Okay. Second derivative is 1 over L square and so on. Okay. Very often in equations we get complicated expressions, okay, where we have for example d by dx is the partial derivative, d by dx is a total derivative. Okay. I will come back and explain what these individually mean, but the dimension of all of these is the same, which is length inverse. Okay. Similarly, the dimension of partial by partial t and d by dt, the dimension is t inverse. Okay. Integral with respect to t has a dimension of time, integral with respect to x, okay, has a dimension of length, okay, because you are integrating with respect to x is dx times something. Okay, so, that integral dx has dimensions of length. Okay. Similarly, integral over volume, the dimension of that is going to be length cubed. And there are other quantities that we will see later. For example, there is a gradient which is equal to Ex d by dx plus Ey d by dy plus Ez d by dz, okay, where Ex, Ey and Ez are unit vectors. This has dimensions of length inverse. A vector has dimensions. Okay. For example, the velocity vector, which I will write with an underline, is Vx Ex plus Vy Ey plus Vz Ez. Okay. The components have dimensions, the unit vectors are dimensionless. Okay. All unit vectors are dimensionless. The components have dimensions. The dimension of the component is the same as the dimension of the vector. Okay, because the unit vectors are dimensionless. Okay. Let me take for example an equation that we will see much later in this course for momentum transfer. It is called the Navier Stokes equations. I will not tell you the meaning of the terms here. I will just explain to you how you can get the dimensions. Okay. So, this is often written as partial v vector by partial t plus v dot grad v is equal to minus grad p plus mu del square v. The dimension of each additive term in this equation is the same, and that is equal to the dimension of the equation. Therefore, I have to express this in terms of additive terms. Okay. How do I do that? I expand out this bracket, rho times partial v by partial t plus rho v dot grad v is equal to minus grad p plus mu del square v. Okay. And now I have to find what is the dimension of each term in this equation. First term, rho partial v by partial t. Density is m L power minus 3. Velocity is L t inverse. Okay. And I have a derivative with respect to time. Therefore, the derivative with respect to time has dimensions t inverse. Okay. And you can easily verify that this is equal to m L power minus 2 t power minus 2. Okay. Second term, rho v dot grad v. Okay. Rho is m L power minus 3. V is L t inverse. Okay. I have another velocity L t inverse, and I have this gradient operator here. Gradient has dimensions I told you of length inverse, because it is a derivative with respect to distance. Okay. And this also has the same dimension m L power minus 2 t power minus 2. Okay. You can easily verify that. Okay. On the right side, gradient of the pressure. Okay. Pressure has dimension of m L inverse t power minus 2, and this gradient is a derivative with respect to length. So, therefore, this has dimensions of L inverse. Okay. This is the same as m L power minus 2 t power minus 2. Okay. And then I have this last term here, dimension of mu del square V. Viscosity, we had derived the dimension m L inverse t inverse, okay, into velocity L t inverse. I have del square, that is 2 derivatives with respect to position, 2 spatial derivatives, therefore, you get L power minus 2 here. Okay. And once again this is equal to m L power minus 2 t power minus 2. Okay. You can see that all terms in this equation have the same dimension, therefore, this equation is dimensionally consistent. Derivatives have dimension, time derivative is 1 over time, spatial derivative is 1 over length, second derivatives are 1 over t square, 1 over L square, and so on. Okay. Integrals have dimension of time, length, and so on. Okay. So long as you put all of those consistently, all terms in the equations have to have the same dimension, and that is the dimension of the equation. Okay. So, I will continue this. We have completed dimensional analysis. Next class we will look at how we can use dimensional analysis to get relations between quantities that we do not yet know. Okay. So, that dimensional analysis for a sphere settling in a fluid I will start in the next lecture. I will see you then.